Well, there's a lot of equations in thermodynamics. One of them that we want to know is delta U. This is the change in total energy or change in internal energy. Internal energy is the total energy. Okay. So now, put it on. Thanks. Delta U. And so the change in internal energy, this is what we want. How much energy are we going to get out of some process? This is going to equal U final minus U initial. But these are called absolute internal energies. Absolute internal energies are difficult to determine accurately. Difficult to determine accurately. The reason is because of chemical potential energy. Where does chemical potential energy? The kinetic energy is easy, E sub K, because remember, U is equal to the kinetic energy plus the potential energy. So EK is not difficult. But PE is difficult. Because how much potential energy is stored in the nucleus? Actually a lot, but what can you break? When we do potential energy, we always have to compare it to something. Potential energy compared to what? For example, there's a lot of potential danger if there are a lot of sharks, but in a tank full of sharks, is there much danger? Probably not. And so we have to compare it to something. If you're a little fish in a tank full of sharks, then there's probably a lot of danger. And so we look at the potential energy of the nucleus, and then we have to think, okay, the potential energy of the nucleus compared to what? Okay, compared to individual protons and neutrons, yes, we can maybe determine that. But then you have the protons, and the protons can be broken up into quarks. Neutrons can be broken up into quarks, and then where does it end? Maybe it ends at quarks because the particle physicists, I think their theory has come a long way and they have a pretty good grasp. But even then, the calculations are not so accurate because the calculations are not so easy to do. And so we never determine the absolute. Instead, we take advantage of the first law of thermodynamics. The first law of thermodynamics says that energy is neither created nor destroyed. And so if the system loses energy, then what must happen to the surroundings? It's got to gain. If the system gains energy, then the surroundings has to lose. And so what we're going to do is we're just going to use the first law of thermodynamics to figure out what our delta U is. So whatever the system is, the surroundings has to be opposite in sign. We have a sign convention, but in an equation like this, the sign just means opposite sign. It doesn't mean it's exothermic. It just means opposite sign. Does not mean exothermic. Just means opposite sign. Yes. So whatever the system is, the surroundings is the opposite. Okay, so we know that the surroundings has to absorb, or the surroundings has to lose energy. And when we look at how the surroundings and systems can exchange energy, it can exchange energy in the form of heat and or work. And so this is the heat exchange between system and surroundings. And this is the work exchanged. Between the system and surroundings. The problem is this. We have something called state versus path functions. A state function depends only on the initial and the final state. Like a change in temperature. A change in temperature only depends on what your initial temperature is and your final temperature. However, a path-dependent function depends on how you do it. Depends on the path. So there are different ways you can get up to the top of the mountain. You know, one way is you can hike up to the top of the mountain. Another way is you could take a helicopter. But it doesn't matter if you're just looking at the initial and the final, if you're at the top of the mountain or not at the top of the mountain. And so whether you hike up, hiking or helicopter riding up to the top of the mountain is what we call a path function, because it's going to depend on the path you take to get up the mountain. And so,
Why are we interested in the work?
The work, why are we interested? We are interested in how much work a chemical reaction can do.
So, like, what is work?
Work, there are different kinds of work. So one type of work is work of like, say, lifting an object. You know, that requires work because we got the gravitational force, and then we got to lift it. It depends on how much it weighs, you know, and how high we lift it, basically. And so that's work.
So, example that I was told is like, if I'm just holding something like this, I'm not doing any work. Good work to get it here, but now I'm not doing work.
Right. So the work is lifting it like this. Now this has gravitational potential energy. And so it's static. So we say this is gravitational potential energy. Now this gravitational potential energy, we can do two things with this. We can convert this into heat, or we can convert this into work, or a combination of the two. So if I have gravitational potential energy like this, I can convert it into, let's say, heat. If I convert it, how could I convert it into heat? Well, one way to convert it into heat is, well, I can try to, is like drop it, and then all that gravitational potential energy is converted into kinetic energy, but that kinetic energy is conserved, it's going to be transferred to the surroundings. So what can happen is the bottom of this might warm up, or a little bit of work. You could hear the sound. Sound is just pushing air molecules. And so that was work, and then there's a little bit of heat. And so we converted the gravitational potential energy into work and heat. But the problem is the amount of work we do and the amount of heat we generate are path-dependent functions. Those depend on how we do it. So, for example, if I tie a rope around this and a pulley and then just slowly lower this with a counterweight, then that's converting most of that energy into work. You know, this would be like a clock, you know, one of those clocks that have the weights that go back and forth like this. Whereas if I had a slide, like a friction surface, then I can slowly slide this down, generating friction, and so the friction generates heat, and then I can convert it into heat. So the gravitational potential energy is a state function. That doesn't change. There's a fixed amount of energy. You know, for it would be 1 joule's worth of energy to lift a kilogram mass by a meter. I don't know how many kilograms this is, but more than a kilogram. That's fixed. Now, how much heat is generated in exchange with the surroundings and how much work is done in exchange with the surroundings depends on how you do it. What path does this take to get back down to the table?
So how is work different like than motion and displacement?
How is work different? No, work is part of motion. Work is a force, on this times distance. So it depends on the distance you have to. Let's say you have to push a car. You have to push a car that broke down, and it depends on how far you push it, and its mass. And so the more you have to do that, the more work you have to do. And so the whole situation comes down to this. And this is why we're interested in the work. This is a state function. So it's like a battery. If you have a battery, the battery has a fixed amount of energy. And so let's say I have a AA battery here. Delta U is always the same. Assuming that we have the same amount of reactants in here. Because a battery converts chemical potential energy into whatever. And so the delta U is the same. It's a AA battery. But are we always going to get the same amount of work or the same amount of heat from this? Well, it depends on where you put the battery in, and that'll dictate how much work and heat. And so even though delta U is fixed, it's going to depend on how we use that energy. And so these are path functions. And so let's say we use this battery to power a little portable heater. And so we can connect this battery, as long as this heater doesn't make any noise. The heater generates heat by the friction. These electrons have to travel through the wire. And the wire has metal atoms that are vibrating like this, and the electrons are trying to get through, and it's causing collisions and friction. And so what happens is we end up generating heat as the electrons try to move through this particular wire. And so in this case, what we want to do is we want to make as much heat as possible. And so in this case, delta U is always the same, delta U. But in this, we want the work to be close to zero. There could be some noise. It could be a noisy heater, and a noisy heater is generating sound. Sound is more mechanical work because you're pushing the air molecules in some kind of pattern. But what we want is the work term to be close to zero. Whereas we can do alternately, we could try to generate as much work as possible by, let's say it's not a cold day, let's say it's just the opposite, it's a very hot day. It's a very hot day, so I have this little portable fan. Uh-huh.
You said that work had to do with motion. Wouldn't like the electrons technically really be considered work?
Mm-hmm. Right.
So
but that work of pushing the electrons through this circuit is going to generate the heat because of the frictional losses.
So the work converts.
Yeah, okay. Right. But there's still, I'm saying it's approximately zero or, minimal. There's going to be some work done.
Most of the work is converted into heat.
Right. Most of the work is converted into heat. In fact, all the work eventually is converted into heat but you got to get the electrons through the circuit. And so that has to be successful.
This is entirely off topic, but are the assignments supposed to be due in one day or?
The assignments are due at 11 at noon, basically.
Okay.
Yeah.
I just wonder because some of them say PM.
And some of them PM. I have to fix that.
So it's due the afternoon of tomorrow?
Yes.
Okay.
I just want to see what you guys have done in preparation for the test, up to that point.
points if I understood it correctly?
Okay, what I'll probably end up doing is I originally had no late credit for the homework, but what I'll probably end up doing is at the end of the semester just collect late homework all at once at the end. It's just mastering Chem is tricky.
Do you think that's easier to track? Like when you get like our grades timely, if you were like.
No, it's not easy to track. It's a pain, but some people have 0 points on the homework. I don't know. I'll give them one chance to get it in.
And is that going to be docked like half credit or full credit?
Well, in the past, I've done 80% credit in the past.
Are you planning to do half?
Yeah, I'll do 80% credit. What did I do last semester?
Oh, I'm not sure.
And does anybody remember, Rory? Do you remember what I did? Or Tanner? Tanner, you guys probably did the homework on time. Let me look. I'll do what I did last semester. No. It's officially supposed to be due at the beginning of class on Wednesday, but I just made it till around noon. I'll probably make it till about 1 p.m.
At the end of class.
Yeah, at the end of class. So it's, what I have to do for mastering is I have to reset all the due dates, which takes a lot of time to reset all those if I collect late homework.
Can you explain how like the change of internal energy in the battery is always the same?
It's always the same because the battery has a certain chemical potential energy. Most batteries operate with zinc and some oxidizer. The oxidizer is usually something like a solid, like manganese 4 oxide or something like that. MnO2 is typical. This isn't a heavy-duty battery. There's a chemical reaction, and this chemical reaction yields the same amount. We end up forming Zn2 plus other stuff.
I was like thinking of it like U is equal to kinetic energy plus potential energy, which would like make sense for me as a battery.
The battery, we always, remember what we do, we always start and end at the same temperature, so there's never any change in kinetic energy. The only change is in potential energy. And so delta U is equal to the delta PE. But how do we determine what delta PE is? Because we do not do absolute. We do not do U final minus U initial. This is not typically done. So when we want to measure how much internal energy changed, we have to know how much heat and how much work was done. These are measured or calculated. Remember, delta KE is plus delta KE, EK or whatever you call it. KE, EK is the same, is 0. So going back to this is work. Would you agree that it takes work to drive a fan motor? Yeah. And so, unfortunately, the fan motor, it can't convert it 100% efficiently. And so there's going to be a little bit of heat. But what we want to do is we want to minimize the amount of heat and maximize the amount of work. And so here it's going to be Q plus W. And so hopefully we can minimize this and maximize this. If we had a fictional frictionless fan, then, and there was no air friction with the blades, then we should be able to maximize. There's going to be air friction here too that's going to generate heat. That's a problem with converting, it's hard to do it efficiently. But would you agree that there are different amounts of heat for the same delta U? The delta U for the portable heater versus the delta U for the fan are the same, but the amount of work we do and the amount of heat we do depends on it depends on what we connect the battery to, but the battery has a fixed amount of energy, and it doesn't change. And so this is the situation here. This is a state function. There's no color coding here. I just forgot to change the color. And these are path functions. And so it's hard to predict. It's hard to predict how much heat you're going to generate, right, in a reaction, because it depends on the path. So the basic problem is it's hard to predict. Unless you know how much work is done. Because Q changes depending on how much work. The more work, the less heat. The less work, the more heat. And so how to make, so to get around this, we do reactions in two ways. One, we do it under constant volume conditions. In constant volume, this is it. Delta U is entirely converted into heat. No work is done. So if we do the reaction inside a bomb, then no work can be done. And to designate this, we call this Q sub V. So normally, this is normalized because it depends on the units here. And so this is one way, but in practice, we would have something like this. We would have delta U is equal to the amount of heat released per, the number of moles. Usually the amount AMT here is in moles. And so we usually get units of kilojoules per mole of reaction. So that's fine, but there's another problem, and the other problem is do you work in a bomb? You don't work in a bomb. So the situation is we don't work in a bomb, we work under constant pressure conditions. Under constant pressure conditions, delta U is equal to Q plus W. Now, there's lots of different types of work that can be done. So, for example, work can equal like lifting a weight, or something. So we have what's called gravitational. Or we could have like mechanical. Gravitational is kind of mechanical work, but we can have like a mechanical motor or something like this, or etc. In order to get a consistent heat, we're going to have to restrict the work, the type of work that we do. So we're going to have to restrict the work so we can make predictions to only the work required to maintain constant pressure. Oops. And do you know what type of work that we have to do in order to maintain constant pressure? What type of work that is? That type of work is called pressure volume work. And the equation for it is work is equal to minus P delta V. So when we have a reaction, we have to expand or contract the volume to accommodate for, like especially gas. You know, if we form gas or if we consume gas, we have to worry about that. And so let's say we go from a liquid to a gas. What's going to happen to the volume? The volume is going to expand. So liquids typically have 1,000 times less volume, or something like that. And so this would be V initial, this would be V final, because the gas now is mostly empty space. And so here, this is like the work of blowing up a balloon. You know, how much work does that take? Well, how much work that takes is this is going to be work done by the system. Work done by the system is the system volume expanded. And so the system blew up the balloon. And that's going to be equal to minus P delta V. We need one conversion factor. So we need to know what delta V is in liters, and we need to know what P is in atmospheres. So we typically have this in atmospheres, we'll have this in liters. And then we know that 1 liter atmosphere is equivalent to 101.3 joules of work or energy.
What does it have the negative sign? Like means opposite?
Negative sign means it loses energy. So V final is bigger, V initial. And so in this case, delta V is greater than 0, which means the volume of the system expanded. And so volume increase, increasing volume. That means who had to blow up the balloon? Who had to blow up the balloon is the system. If the system blows up the balloon, then the system's going to lose energy. If you had to blow up a balloon, you'd lose energy, right? In blowing up the balloon. And so that's what the negative sign means. This negative sign means there was some loss of energy. And so the delta V is positive, P is positive, therefore the work is negative.
How can we tell when, like, either the system or the surrounding is using the energy?
By the sign. So here, the system does work. The work of the system is negative. What this means is work of the system is negative, that is less than 0. Therefore, the system loses energy doing works. If the system loses energy doing work, then we may not get as much heat, you know. Uh-huh.
So the sign is always supposed to be based on like the perspective of the system.
Yeah, if I write system here, yeah. We could also do it from the surroundings perspective, because if the system loses energy, where did that energy go? Because the energies it went into the surroundings. So the work of the surroundings will be positive, and the system will be negative. This is for the first law of thermodynamics. This is constant pressure. This is in order to maintain constant pressure. If we're forming a gas, the volume has to expand, otherwise the pressure is going to increase. If we keep the volume constant, like the V initial here, V initial is equal to V final, and we form a gas, then the pressure is going to increase, and we have a bomb situation, a pressure bomb situation. And so under constant pressure, this is what we're looking at. Under constant pressure, okay, that scenario, system does work.
Constant pressure.
Yeah. The system does no or negligible work. Let's say we have A, which is a liquid, plus B, which is a solid. And this goes to C, which is a solid, and D, which is a liquid. You know, there's going to be small changes in density, but those changes in density are very small. You know, do you think it's a liter's worth of change? So if you go from, let's say, one liquid to another, do you think the volume is going to expand by a liter or contract by a liter? Now, to expand the volume by a liter is 100 joules. Is 100 joules very much? It turns out it's not very much when we look at chemical reactions. When we look at chemical reactions, they're typically like 1,000 joules. You know, even 1,000 joules, you know, like 1,000 kilojoules. So if we're looking at 1,000 kilojoules and we have 0.001 kilojoule, is 0.001 kilojoule going to make much of a difference in 1,000 kilojoules? Yeah, so some people ignore it completely, other people will calculate it. I've done both, I could do, but it turns out, you know, it kind of rounds off at the end. So your book says just look at delta N of gas. You know,
I have a question that isn't like related to this, but like in the homework it says something about how they can increase pressure when amount of moles increases. Is that true?
Yeah, if the pressure increases in the constant volume, then the amount of moles of gas increases. That's usually what we do. I mean, it could increase based on this, you know, but just slightly, ever so slightly, it could increase like this. And so your book focuses on just looking at delta N of gas. Delta N of gas here is +1. We go from 0 moles of gas on the left to 1 mole of gas on the right, so that's +1. We could go +2, +3, which would result in higher pressure increases.
Sorry, did you say that at an increase of pressure at constant volume, the moles increase?
At constant volume, yeah. The only way we're going to have pressure increases and pressure decreases is if we're working under constant volume. If we're working under constant pressure, the pressure never changes. The volume will expand and contract to make up for it. Under constant volume conditions, the volume can't change. So if we have gases formed or gases consumed, it's going to result in big changes in pressure because the volume change should be big, significant.
What is a bomb? Is a bomb constantly changing the pressure but maintaining
Yes,
the volume?
right, a bomb. It depends on the reaction itself. Some reactions, you don't have to worry. Like this reaction, if I did this in a bomb, would I worry about a pressure explosion? I would not worry about a pressure explosion because what is delta N of gas? Delta N of gas is 0. So we're going from 1 mole solid to another mole solid, and the density might change a little bit, and then we're going from 1 mole liquid to 1 mole liquid. The density there might change a little bit depending on what new liquid and new solid we form. But the volume change is negligible in that case, so that's why the book only looks at delta N of gas. The book looks at delta N of gas because there you're going to see a significant change, because the work involved is kind of a small number compared to the chemical potential energy change involved. And so here, delta N of gas is 0. There's no change in the moles of gas. Therefore, the volume doesn't change. If delta N of gas is 0, then what we say is that delta V is approximately 0. And therefore, the work of the system is equal to minus P delta V, which is going to be about 0. Here.
Gases for moles, so number of moles.
Yes, right. System does no work. So if I did this in a bomb, I wouldn't worry. You know, you could have the flimsiest bomb, and it's not going to generate a pressure bomb, pressure explosion. Or you do this out in the open lab. If I did this in a bomb, yes, the pressure is going to increase dramatically if I did this in a bomb.
To explode a bomb with the right.
I'm sorry?
You explode something.
Yeah, you could explode. In fact, a bomb did explode in Hawaii, at the University of Hawaii. I think a person was doing something, and then they had hydrogen, and then it exploded in the laboratory, killing the student or the researcher. This happened like 3, 4, 5 years ago. Unfortunately, the aftermath of it.
So, since the pressures inside of the bomb are changed,
If delta N of gas is not 0,
okay.
2015, so it was actually 9 years ago. Look at the damage. Yeah, it's really unfortunate. This is blood, unfortunately. But yeah, this is the accident scene. Usually when you work with things like this, you have an explosion shield. They make explosion shields that you can put in front. And so most labs have an explosion shield if you're working with anything that's potentially explosive. I don't know if this person was working with an explosion shield. It's pretty unfortunate. This is redox. Redox reactions, you don't have to, like if you're doing an acid-base neutralization, do you worry about not walking out after lab, you know? But if you're doing redox, you got to worry about it. You know, you got to worry, am I going to lose fingers? Am I going to lose, you know, you can do something that's going to be potentially. This is why when I thought, you know, when I was thinking about hydrogen cars, I was thinking, no, I don't want hydrogen cars on the road, you know, because these are all potential bombs, you know, not pressure bombs, but energy. But apparently they're safe enough, you know, so they pass. Probably am overly concerned about it, but I shouldn't be. Okay, not system, sorry, surroundings. So here we have V initial of the system, and then here we have V final of the system. So here in this case, delta V is going to be less than 0 for the system. Therefore, delta V of the surroundings is greater than 0. And so who blew up the work? The surroundings does the work. And what that means is the system gains energy. And so what we'll have here is this. Work is equal to minus, this is work of the system, is equal to minus P delta V. And a delta V is negative, and then we have this negative times negative means that the work is going to be greater than 0. And so the system is going to gain energy based on that. So what we're going to do is we restrict, again, we're going to restrict the work. is restricted to the natural work of a chemical reaction done under constant pressure conditions. You know, if you do this under constant pressure, the gases got to expand, or gases have to contract, you know, volume. So again, work is restricted to the natural work of a chemical reaction. That is P delta V minus P delta V. And so here we have delta U is equal to Q plus W. And so we're going to do this under constant pressure. And therefore, we're measuring Q sub P specifically. And so we shouldn't mix it up with QV. Plus the work of the chemical reaction. The work of the chemical reaction is going to be minus P delta V work only. So we aren't going to have mechanical work. I mean, mechanical in the sense of driving a motor or whatever else, doing that. Now, QP is going to equal delta U minus the work. Delta U is a state function, and so we always get the same amount of energy. Work here, now this is minus P delta V work. If I have a change in pressure, you know, let's say the pressure went from 1 atmosphere to 2 atmospheres. Does it depend on how it gets there, like delta P? What is delta P equal to? If my final pressure is 2 atmospheres and my initial pressure was 1 atmosphere, then the change in pressure would be 1 atmosphere. It doesn't matter how it gets there. That's a state function. So P is a state function as well, but we're not looking at delta P. But we are looking at delta V. So these are state functions. It doesn't matter if I have a change in volume. I go from 1 liter to 2 liter, then delta V is always 1 liter. Does it matter how I get from 1 liter to 2 liters for my delta V? No, I could go from 1 liter to 1,000,000 liters and back to 2 liters. My delta V is still 1 liter. Or I can go from 1 liter straight to 2 liters. My delta V is still 1 liter. So these are state functions. So what that does is it makes Q, you know, this is normally what we call a path-dependent function. It makes Q into a state function. So now Q is a state function. And so this is critical here. What we need to do is we need to make Q into state function. How do you make Q into state function? You always do the same amount of work, you know, for reaction. And so each time we do the reaction, we do the same amount of work. Well, what work is that? That's the natural work of the chemical reaction. Therefore, we're not going to call Q anymore because it's different. Normally, Q is a path function. And so what we're going to do is we're going to define a new state function.
What does the P stand for?
Constant pressure. Define a new state function. And this new state function is called delta H. H is enthalpy. And delta H is equal to delta U minus W. But W is P delta V work only. Remember, we had to restrict it. And so this is going to be delta U, so I'll put a little asterisk here, minus P delta V. And so what I call this is like this on the video. I called this your net energy. And I called this delta U your gross. So if you've ever gotten a paycheck, you know that, let's say you're expecting $1,000 on your paycheck, but your take-home pay is less. Why is your take-home pay less than $1,000? Because there are withholdings, withholdings for tax, withholdings for various things, Social Security, disability. There are all a bunch of withholdings. And so even though you expect to gross $1,000, you actually net less than $1,000 because of what we call taxes and withholdings. And so the work here,
So would it be like And then another type of equation would be delta H is equal to parentheses Q plus W minus P delta V.
Delta H, delta H is, you're saying Q plus W minus P delta V?
Yeah. No, yeah, but like in parentheses.
Q plus W in parentheses? Yeah, this is our normal. This is delta U. Delta U is equal to Q plus W. These are all relationships that we do. These are called thermodynamic relationships. So yeah, this equation's okay. You know, if you want to use that. In thermodynamics, you have to come up with all these relationships, and you have to be able to manipulate all the equations. But for us, we don't have to do that.
Wait, so the equation is
Yes.
is it supposed to be double negative? Like,
This one?
yeah.
Yeah, because the work is minus P delta V. And so this is delta U minus the work, which is minus P delta V. So your book is going to put it positive, but I don't put it positive for my own reason. Because when we calculate the work itself is minus P delta V. So what I do is I don't want to get mixed up with the signs. So the more variations I see, like here, I see it as plus P delta V. So then I get confused. Is it plus P delta V or is it minus P delta V? So if I always write it minus P delta V, then I don't get it confused. And so, your book is going to write it like this.
How does Q, I guess Q
But,
becomes,
whatever way you want to write it, it's fine. Mhm.
how does Q, like, heat become a state function by like doing the same?
The state function means that you always get the same amount of heat no matter how you do it. So if you always do the same amount of work, P delta V, then you always get the same amount of heat. We just have to make sure we always do the same amount of work. That is, we can't allow the pressure to change. If the pressure changes, let's say, it changed a little bit, then all of a sudden we aren't going to get the same amount of heat. So let's say at the start of the reaction, the pressure was 1 atmosphere. At the end of the reaction, the pressure was 1.2 atmospheres. Then it's no longer a state function because the pressure changed. Delta H, you can never use delta H. A lot of people think, okay, I can use delta H for anything. You can't use delta H for anything. If you did the reaction in a bomb, delta H is totally meaningless. Because unless there's normally no volume change. So we'll look at it, this scenario. So delta H is very restricted. You can use delta H when you have constant pressure and only one type of work is done. If you start doing other types of work, you're going to get different amounts of heat. But we need some reference point. Of course, if you do other types of work, it's no big deal. We can calculate it, but you need other equations to calculate it. If you want to use these equations, then you have to restrict yourself to these conditions. And so the two easiest restrictions to do is constant volume, bomb, and constant pressure with only P delta V work. We're always going to get the same amount of heat in the bomb. It's QV, which is equal to delta U. And if we do it under constant pressure, we'll always get the same amount of heat, which is QP. The problem is that QP and QV are not always the same. So we only allow P delta V work, otherwise it's going to screw up our calculations. So this is the most important for us. Delta H is going to be much more useful than delta U. Much more usable. Let's see. But bomb calorimetry is the only option for some reactions. You can't do some reactions in a coffee cup. It's just not practical at all. And so from bomb calorimetry, we measure QV, and QV is equal to delta U. And so we have to see how they relate. How does delta U and QV relate to delta H? Uh-huh.
So this is going to be another hard example. How complex would you say like the hydrodynamic expression is?
How complex is it?
Yeah. An example.
Well, we can look at it. You can look at it. This is not that bad here, I think. We'll see. I don't know what you guys think of this here, but we'll take a look at this here. So delta U is equal to Q plus W. And the W here is minus P delta V. So let's say we do this under constant pressure, and delta V is equal to 0 or close to 0. So delta V is equal to 0. If delta V is equal to 0, then the work is equal to 0. And so as long as this is under constant pressure, Q sub P, and if the work goes to 0, then delta U and delta H are the same. So we just have to look, under constant pressure, was there a change in the volume? The change in the volume is going to be given by delta N of gas. If delta N of gas is 0, then delta V, we can say, is close enough to 0, which means the work is 0, and then nothing happens. This is a case where, we go from a solid to solid, or liquid to liquid, or gas to gas. An example of this would be, let's say we go from 2 moles of gas, A gas, to 2 moles of B gas. So we start with 2 moles of gas, which is about 50 liters, and we end up with 2 moles of gas, which is about 50 liters. Was there much change in volume? No, there was no change in volume. If there's no change in volume, then there's no work done. This has to be under constant pressure conditions. Delta U is always equal to QV, and so this is always the same. It's equal to QV, or it's equal to QP plus W. So we have that.
Sorry, what's delta N gas again?
Delta N gas is, you look at how many moles of gas you have on the product side. So over here we have 2 moles of gas. So this is N final equals 2 moles. And then we look at the initial. N initial equals 2 moles. So
change in moles?
Yeah, it's the change in moles of gas from the balanced equation. So delta N of gas would be 0 in this case. There's no change in the moles of gas.
So
Mhm.
this example is on a constant volume and so it's the volume.
No, no, I wrote QV because delta U is going to be fixed here. To avoid this confusion, let's do this. Let's eliminate that. This is going to be under constant pressure here. And so another scenario is this. If you do this reaction under constant pressure, so this is when we have delta N of gas is 0 here. Another scenario is if we have delta N of gas that's going to be greater than 0. So we're going to form some gas. So we look at U initial and U final here, and we're going to be forming gas. If we form gas, then what's the work going to be? The work is going to be minus P delta V. And what should happen to the volume if we're increasing the number of moles of gas? It should increase. If it increases, then the work, well, if it increases, then delta V is positive, right? Delta V is going to be greater than 0, which means the work is going to be altogether negative. Now, if this is an exothermic reaction, then delta U is the same here. And we could get delta U from Baum. And so that's why I wrote delta U is QV. But over here, now we look here, and what we're going to get is Q plus W. So delta U is equal to Q plus W. This is my delta U. And then I'll do Q maybe in red. And then W in blue here. And so it depends on how much work is done, but it's going to be fixed depending on how many liters of volume change we had. And so typically the heat part is going to be quite a bit bigger here. And so this will be my Q here, this arrow. And then this will be my W here, this arrow. So in this case, since the system does work here, are we going to get as much heat evolved from the reaction? No. And so here, if we're doing this under constant pressure with only P delta V work, then we can call the heat QP. And then QP is equal to R delta H. So how do you want to say this? Do you want to say that delta U is greater than delta H, or what do you want to say? So how does delta U and delta H compare? So which one is the bigger drop, delta U or delta H? Delta U? And so what should we say? Should we say that delta U is greater than delta H? In this case. Over here, delta U and delta H were the same because there's no work. So all of that was converted into heat. If we just are looking at delta N of gas, there's no change in the system volume. But over here, what should we say? Delta U is greater than delta H. It's a bigger drop. You know, so this might be a 1,000-foot waterfall. This is a 900-foot waterfall, something like that. Does that make sense?
What does this diagram represent? What is a drop?
This would be, let's say we don't have the absolute internal energies here. We're just looking at the change in internal energy here. So let's say let's say delta U were 1,000, just for an example, 1,000 kilojoules here. And let's say we did, although this would be a bit extreme, 100 kilojoules worth of work. If we did 100 kilojoules worth of work, then how much heat would we get out of this 1,000 kilojoules of internal energy change? Would we get all? This is like, let's say your paycheck were $1,000. Your paycheck, so you're expecting $1,000. This is minus $1,000. So the system, you're the surroundings. You're expecting $1,000 from the system. Are you going to get a full $1,000 from the system? No, you're not going to get a full $1,000 from the system because there was some work involved. And that work involved is 100 kilojoules. And therefore, you're going to get less. How much less? 900 kilojoules. Does that make sense there? And so this is a scenario where we have this. Delta H is your net, and then delta U, okay, minus the work. And the work we restricted, so I'll put a little asterisk there. And so the work here is, there's no work done. So what I call that is, let's say that would be like no tax. You know, on certain days you can go shopping and you just pay the sticker price or the tag price, and they pay the tax. And so there's no tax here. And so if you expect $1,000 as the surroundings, so let's say minus 1,000 kilojoules, you end up getting a minus 1,000 kilojoules. And so there was no withholding. Over here, we have our delta H is equal to delta U, okay, minus W here. But in this case, this is a tax. It's a tax. You can't avoid this tax because if delta N of gas is greater than 0, the system volume has to expand. And therefore, work has to be done. And so this is unavoidable, this tax. All right, let me pause.
So just to be if delta N gas is greater than 0, volume has to expand, and work has to be done, so then you have to subtract work from your delta U.
Yeah. If delta N of gas is greater than 0, in order to maintain constant pressure, the volume has to expand. If the volume has to expand, the system volume has to expand, then work was done. Okay, I think Word has crashed. So just getting back to this, the gross here drop is delta U. That's a minus, let's say, 1,000 kilojoules or $1,000 that the surroundings expects to gain. But how much actually does the surroundings get? And you're the surroundings, let's say. How much the surroundings get is going to be dictated by how much work. And so this is our QP, which is our delta H. And so just for an example, let's say the delta H was 900 kilojoules because 100 kilojoules was used to expand the volume, just to keep the numbers simple. And so the work of the system here is minus 100 kilojoules. And so altogether, this is minus 1,000 kilojoules. So this is what I was saying, you could think of as your tax here. So delta H, which is your net, is equal to delta U, which is your gross, minus this work tax that was done in this case here. And so what we say here is that delta H is going to be less than delta U, but this gets confusing because here, when we look at this, minus 900 kilojoules is our delta H, but when we look at our delta U, it's minus 1,000 kilojoules. And so some people get confused because when they think about this, just as numbers alone, what's a smaller number, minus 900 or minus 1,000? And which one's a bigger number? And so what some people do is they'll just say, if we take the absolute value of something, then we'll see, because energy is always positive, and the negative and the positive is not, is not there for, its position on the number line. It's there to tell us the direction of change, And so which one has a bigger direction of change? The direction of change here is negative, means that somebody's losing. And if this is the system, that means the system's losing here. and the surroundings gaining. So the direction of change. And so if we look at that, then which one's the bigger direction? Well, it's going to be the minus 1,000. It's going to be bigger. So delta H is going to be less. It's going to give us less heat to the surroundings. All right, if we look at another exothermic reaction, I'll just try to do this here. Okay, but let's say delta N of the gas in this case is less than 0. And so some gas is consumed during the course of this reaction. So the gross is the same. It's going to be minus 1,000 kilojoules here, gross. But now, when we look at the work of the system is going to be minus P delta V of the system. Well, if the system volume contracts, the surroundings volume increases. But anyway, delta V of the system is going to be less than 0, which is a negative. And so negative times a negative gives us a positive. So this is positive. In other words, it's going to be greater than 0. And so what that means is if the work is greater than 0, then this is going to result in an up arrow here, as now the work is positive. And so let's say it's positive 100 kilojoules of work was done by the surroundings onto the system. And therefore, the heat is going to look like this. It's going to go down even further because we have to go back up here to get to our final state in this particular state function. And so this is going to be our QP here. Our QP under these conditions is our delta H. And so what is our delta H in this case? Here. Our delta H is minus 1,100 kilojoules. So when we look at the internal energies, the total energy change here is 1,000 kilojoules. How are we getting more than the total energy? And the way we're getting more than the total energy is we're looking at how the surroundings interacts with this. And so when we look at this, and we aren't going to measure these, the absolute enthalpies, which would be this, the absolute enthalpy is equal to the absolute internal energy. This comes from just the delta H is equal to delta U plus P delta V. But if we look at this is H is equal to U, this would be H initial, is equal to U initial, plus P's constant, V initial. So we don't determine these because it's the same problem with internal energy. The absolute internal energies, because of the potential energy terms, difficult to determine. And then we have H final. H final is going to equal U final plus P V final. And so we're adding the pressure volume state. The pressure volume state is related to energy in terms of PV work here to this. And so we'll have the internal energy plus its pressure volume so we can see how it interacts with the surroundings in terms of volume expansion and volume contraction. So that's another way. So in this case, delta H is what we're going to say is greater than delta U. Because delta H here, we're going to get more energy or more heat out of this. We're going to get 1,100 kilojoules versus our total energy change, internal energy change, 1,000 kilojoules. And that's due to the surroundings. The surroundings doing work on the system. So the surroundings does work on the system, and the system gains from that. Uh-huh.
Do you need to know the absolute enthalpy thing?
No. The question was, do you need to know the absolute enthalpy? No. We're not going to do any of these calculations here for that.
So just the main thing is like...
The main thing is this, and so the main thing is this. So we looked at 3 scenarios here. The first scenario is delta H when there was no work done. And so delta H is equal to delta U minus W. And so the first scenario was where the work was 0 under constant pressure conditions. This is to summarize what I just said. And so under constant pressure conditions, if there's no work because delta V is 0, because delta N of gas is 0, then there's no tax. And so this is like tax-free day. What you see is what you get, basically. And so no tax. The second scenario is where we had a tax because the system volume had to expand. So in we'll call it scenario 1. In scenario 2 above, we had a tax. The work was actually less than 0. That means the system had to lose energy doing the work, and that means delta V of the system, delta V of the system was 0, and delta N of the gas is 0. Delta V of the system is greater than 0. That is, the volume expanded for the system, and that means delta N of the gas is greater than 0 here. The third scenario we had was that delta H is equal to delta U minus W, where W is a bonus. The bonus comes from the surroundings. And this is what we track that with the PV, initial PV state and the final PV state. And so this is the work of the system would be greater than 0. That means the surroundings is giving energy to the system, so the system's gaining that energy. So delta V of the system is less than 0, the volume is contracting, and therefore delta N of the gas is less than 0 here. And so those are the three scenarios. So the types of questions we do are both qualitative and quantitative questions. And so typically, let's say if you have a reaction in a bomb calorimeter, we want to know is, are we going to get more heat or less heat if we do it under constant pressure conditions? Mm-hmm. And so we'll take a look at different reactions. So first we'll do this qualitatively. So let's take a look at some examples here, qualitative examples. And so let's look at this reaction, methane combustion. So I'll take 1 mole of methane gas plus 2 moles of oxygen gas. This has higher chemical potential energy than CO2 and water. So this is going to form CO2 gas and 2 H2O liquids. Okay, and then we're going to have a delta U for this, and we're going to do this in a bomb. And so we'll combust the methane in a bomb. And so delta U for this is just going to be, well, there's no work done in a bomb because the volumes can't expand or contract. And so we're going to say that all the energy, internal energy, and this is chemical potential energy because we're going to start this at 25 degrees C, and we're going to end this at 25 degrees C. And so all that internal energy was converted into a change in potential energy, and that's going to be given off to the surroundings as heat in this case. And the heat, the bomb will warm up, the bomb calorimeter will warm up. And so this is QV that we measure. But we don't burn methane in a bomb usually. What we do is we burn methane under constant pressure conditions. So under constant pressure conditions, will we get the same amount of heat? And so the question is this going to be the same amount of heat as if we burn this under constant pressure conditions, or will we get a different amount of heat? And if we get a different amount of heat, are we going to get more heat or less heat to the surroundings? You're the surrounding. So what we want to do is we want to warm up a pot of water. If we want to warm up a pot of water, will we get more heat trying to warm up the pot of water in a bomb, or would we get more heat trying to warm up a pot of water in your kitchen? So what we need to do is to determine if there's going to be any work under constant pressure. What do we look for? We look for delta N of gas. So in this particular reaction, do we have any change in moles of gas here? Yes? Well, it looks like I have 1 mole of methane gas and 2 moles of oxygen gas. So that gives us a total of 3 moles of gas. 3 moles of gas under room temperature and atmosphere is about 75 liters, right? And then I have, on the product side, I have 1 mole of CO2 gas, and then the liquid at 20, is H2O gas at 25 degrees or liquid at 25 degrees? The liquid, so this is liquid. So delta N of gas is, we look at the number of product moles of gas, 1, minus the number of reactant moles of gas, 3. And so what is delta N of gas? -2. So which scenario is that? Well, if it's -2, then who's doing the work under constant pressure? This means that in order to maintain constant pressure, because over here, what's going to happen? The volume should collapse, but it can't collapse. And so we run the risk of not a bomb, but an implosion occurring here. So if it's not strong enough, we'll have an implosion, but this is going to be heavy steel walled, so we don't have to worry about an implosion happening here. But if we do this in an open lab, yeah, there's going to be an implosion, but you're not going to feel the implosion because what's going to happen, the surroundings will expand and to compensate for that. And so what we have is delta N of gas is -2. So is that, when we look at delta H, which is delta U minus the work, is the work going to be a tax or no tax or a bonus? So it's going to be a bonus. So what we would expect is more heat or less heat to the surroundings in this particular reaction. More heat? So look at those three scenarios. So that was for exothermic. Maybe we should do endothermic as well. But we would expect, okay, in this case, who does the work? So I'd like to look at the internal energy diagram, so U. So who does the work? If we did this under constant pressure, and the volume contracts, and so what this means is delta V is less than 0, then who does the work here? Who blew up the balloon? Whose volume had to expand? Did the system's volume have to expand or the surroundings? The surroundings. So the surroundings would blow up the balloon. If the surroundings blows up the balloon, then who does the work? The surroundings or the system? The surroundings.
When the work of the system is greater than 0?
Well, the one way to think about it is if the system does work and we're looking at this, then the system loses energy doing the work. So if the system does the work, we lose energy. And so we might start off at this energy. The system does work, we lose energy here. If the surroundings does work, then we gain energy. And so the other scenario is like this. If the surroundings does the work, we're going to gain energy like that. And so work of the system is going to be greater than 0, and the surroundings does work.
So when the work of the system is greater than 0, the surroundings does it?
When the work of the system is greater than 0, the surroundings does the work. And the other scenario is when the work is equal to 0. There's no work done, and so it's just flat here. There's no change in internal energy. Mm-hmm. Mm-hmm. Yeah, this is from the sign convention. So if the work of the system is less than 0, then the system loses energy. Why does it lose energy? It loses energy because they had to do the work to expand the volume. System loses energy. And so when we look at it, the work is equal to minus P delta V. So if delta V is positive, pressure is always positive. Therefore, a minus times a positive is going to give us a minus. The minus is going to be, well, that's going to be less than 0. And so what we say is it's losing work. That is, it's losing energy doing the work. So if we start off with an internal energy here and the system does work, it's losing energy, going down in energy here because it's doing work. Does that make sense there?
Wait,
Uh-huh.
so,
So for,
sorry.
Oh, go ahead, Rebecca.
for a question then, like on exam or something, would this be like a conceptual question?
Yeah, it would be a conceptual question. So I gave you some conceptual questions on the exam. I mean, the conceptual questions were with delta H and delta U. You know, which one would you expect to be larger? Is this making sense at all from the previous,
There's no harm
the
in
supplemental?
that much work.
And so we have three, basically we'll have 6 scenarios, which we'll look at just quickly, since I don't have much time here. But this is it, and that's going to change the amount of heat, because when we look at delta U is equal to Q plus W. And then if we do this under constant pressure conditions, so we're looking at QP or delta H. So delta U is equal to delta H, you know, and then we plug in the work term here. But what I'll do is I'm just going to leave it here. Delta H plus W, and then we look, okay, you know, we look at delta H here. So if delta U is exothermic here, you know, so we look at these 3 scenarios. Let me just do this again. So we look at delta U versus delta H. No work under constant pressure. That is, delta N of gas is 0. And so we have delta N of gas is 0. No work is done. So delta U and delta H are the same thing. Okay, let's go to delta N of gas is greater than 0. So that means we're increasing the number of moles of gas. That means work is going to be done. If work is done, is it negative or is it positive? The sign, we have to keep track of the sign. We have to be very careful with the sign. You know, if delta N of gas is greater than 0, then that means delta V is positive. And pressure is always positive, and that means the work is negative. And so we're going to lose energy doing work here. And that means we're going to get less heat. And so this will be our delta H. So our delta H is smaller. We'll get less heat than our delta U. Our delta U is the whole drop. And that doesn't change here. And so this is our delta U here. And so when delta N of gas was 0 again, it's all delta H. If we do work, the other scenario here is if the surroundings does the work. If the surroundings does the work, the system benefits from that. And so the work is actually positive here. And therefore, delta H is greater. Because they have to add up to delta U. And so this will be our delta H here. And so the 3 scenarios for these exothermic, if you're the surroundings and you want to know how much heat you're going to get, delta U is going to be equal to delta H if there's no change in moles of gas. If there's a change in moles of gas and it's positive, then delta U is going to be greater than delta H, or delta H is less than delta U. And then over here, if delta N of gas is less than 0, the surroundings does the work. And so delta H is going to be greater than delta U. We're going to get more heat under this scenario. So when we burn methane, we'll get more heat doing it under constant pressure conditions than constant volume conditions to the surroundings. Does that make sense there? So those are at least focus on understanding these 3 scenarios here. And therefore, what we can do is we can calculate the work. But one of the problems on the practice exam was calculating the work using P delta V, and then just using this equation here to determine it. Oops, I just did the wrong thing. And so that was a multiple choice question. You're just going to use this equation to determine it. Or you could use this equation to determine delta U is equal to delta H minus W.
So in that example with the methane, it's going to generate more heat.
Yes. In the example for methane, we get more heat to the surroundings burning it under constant pressure than under constant volume. And that's, but when you do calorimetry, you're not going to do calorimetry methane combustion in the coffee cup type scenario.
Is it because at constant volume, it would mean that delta H and delta U are the same?
Under what?
At constant volume, would mean that
Yeah,
delta
well,
U and delta H.
always. No. Under constant volume, we have to look because constant volume forces no work to be done either way. And so it may be the same if delta N, you have to look at delta N of gas. If delta N of gas is 0, then delta H and delta U are the same under constant volume condition.
Because they just said that at a constant volume, then that means the work is 0 because they're going to be a change in volume. So that's why I like put it to the first example.
Yeah, but that's QV. What delta H is